Hello everyone, welcome to our last usual Quantum Club talk. Why do I say usual? Because we have one last surprise before the end of the semester. You may have seen in the back, we will have a conference of Fabrizio Buccella. I think many of you already know him. So it will be the 18th of December, so we hope to see many of you there. It will be in the A300. I hope we will have enough seats for everybody. And so, it's the last, as I said, usual Quantum Club talk that we do. Tonight is a talk from Romain Vasseur, so thank you very much for that. And as usually, we give the opportunity for a student to give a warm-up talk, and tonight it's given by Mathias Dupont, which is a master student of Romain Vasseur. And also another important thing, the 8th of December, there will be another event organized by IBM, and so we also collaborate a bit. We help them to organize it here. So you will get information on our website, I guess, and also on the WhatsApp group. Voilà, so Mathias, the floor is yours. Thank you very much.
So, thank you, Elliot, for the introduction. So, before the talk of Romain, I will just make a quick introduction and maybe a reminder about qubits, so the building blocks of quantum information, and about entanglement, one bizarre property of quantum mechanics. But before going to qubits, let me remind you how we encode classical information. So for classical information, we use what we call bits. So it consists of two states, 0 and 1. And with these two states, with sequence of 0 and 1s, we can encode every classical information you can think about. So for example, the word hello, you can encode it like this using a certain convention. And similarly to that, we can encode every information, every book you think about. But what about quantum information? So quantum information, we have a kind of an equivalent of the classical bits. That's the quantum bit that we call qubits. And for that, we use two-level quantum systems. And we have then two states, 0 and 1. So it could be, for example, a spin 1/2 particle or a two-level atom. And so we label the two states 0 and 1 very similarly to the classical bits. So before we were in classical mechanics, this state obeys the Schrödinger equation with h the Hamiltonian of the system we consider. And you can see that this equation is linear. That means that if we have a linear combination of 0 and 1, so linear combination of solutions, this will also be a solution of the Schrödinger equation. So that means that it will be also an allowed state for the system. So for example, we have state that we call superposed. That would be alpha 0 plus beta 1 with alpha and beta complex numbers. So it's just one qubit that has this very special state that is 0 and 1 at the same time. So it's not, in the classical world, we cannot have that. So it's very special of quantum mechanics. And one condition about this alpha and beta is that the norm squared of the two sum to 1. But then even with this condition, we have an infinite number of different qubits that we can make. So that's very impressive. But then what do these alpha and beta represent? So for that, we have to look at quantum measurements. So let's say we want to measure our state here, so an arbitrary qubit. So in quantum mechanics, measurements are associated with operators. So for example, let's say we want to measure sigma z, that will correspond for a spin 1/2 particle to measure the spin in the z direction, for example. So each time we have an operator, we have to look at the eigenvalues of this operator. So here it's very easy, just 1 and -1. And so the eigenvectors are just 0 and 1, so just the basis vectors. And so the eigenvalue are the outcome of the measurement. So when I will make the measurement, I will get or +1 or -1. And the probability to have that, so the probability to have +1 is given by the Born rule and will just be norm of alpha squared. And similarly, the probability for -1 will be norm of beta squared. So we can see that these coefficients alpha and beta are linked to probabilities of outcomes. But it's not like in a classical world we could say, okay, I don't know really the state, I have a certain probability to have 0 or a certain probability to have 1, and when I measure I get 0 or 1. But it's not like this. In the classical, in quantum mechanics, the state is really both at the same time. It's only when we make the measurement that it goes to one of these two states, but we cannot predict in advance which one we'll have. It's not that we don't know, it's like this. So let's say now we want to measure with another operator. So for example, sigma x, we have different eigenvectors, we call plus and minus, just combination of 0 and 1. And we have then the same eigenvalue, +1 or -1. And this one, and this time, we have different probabilities. So for plus, we have 1/2 alpha plus beta square, or for minus, alpha minus beta square. So we see that depending on which operator, we have different combination of these alpha and betas that will enter, but they are always linked to the probabilities. And also, we see that it's important that the sum is 1 because the probability should be 1 to have an outcome. So that's why we had the condition that alpha squared plus beta squared gives 1. So what happens then after the measurement? So we had our state 0 plus 1, and let's say, one postulate of quantum mechanics is that the state after the measurement will collapse to the eigenvector corresponding to the outcome we had. So let's say, for example, we had our state, we measure sigma z, and we get outcome +1. Then at the end, the state after the measurement would just be 0. And similarly, if we measure sigma x, the state after the measurement would be plus. So that's really a non-trivial effect on the state that we had before. So before we had like some information, and at the end, we lose some information about the initial state because we lose these alpha and betas, they are fixed after the measurement. So for example, here we have just alpha equal to 1 and beta equal to 0, or etc. So we see that it's not like in the classical world where we can measure things without disturbing the system. Here measurement will impact the system we measure. And then, so we see at the beginning that we have a lot of different qubits possible. So we could say that we could encode an infinite number of information in just one qubit. For each different alpha and betas, we associate a different information. But in fact, the thing that is difficult, as we've seen before when we measure the qubit, we destroy some of the information. And that will prevent us from extracting all this information from the qubits with only one measurement. So this is because it's impossible to distinguish non-orthogonal states with just one measurement. Let's say, for example, I know that I have all the state 0 or the state plus, but I don't know which one, and I make a measurement with sigma z and I get outcome +1. Then I cannot say if I had 0 or if I had plus, because in plus there is a part that is linked to 0, so I can get the outcome plus also with +1 with plus. So this impossibility to distinguish the non-orthogonal state with one measurement prevent us from extracting more information in qubits than just at classical bits, because if states are orthogonal, like 0 and 1, then we can distinguish them with the measurement sigma z, but otherwise we cannot. But then, so what's the point of using qubits instead of classical bits if we can only extract like classical bits from these qubits? In fact, it's the whole field of quantum computation that deals with that, and that really use this quantum state, like making operation to, at the end, extract this classical information that we couldn't have as efficiently classically But yeah, let me illustrate that with a small example that's called Dutch problem. So in this problem, we are given a function f that takes 0, 1 and gives 0, 1. And we know that this function either way is constant, so gives always the same outcome, always balanced, meaning that once it will give 0, the other time it gives 1. So the goal is to determine if the function is constant or balanced. So classically, we'll just need to evaluate this function twice, and then we know if it's balanced or constant. But using qubits, we can evaluate the function only once. So here is the circuit. I won't explain in details, but the important part is that we evaluate the function only once, and at the end, we measure one of the qubits, and with outcome 0, we know that the function is constant. With the outcome 1, the function is balanced. So we see that using these qubits, we could extract an information, a classical information, that more efficiently than with just classical bits. So there are more sophisticated algorithms that can that allows to get really faster results than in the classical case, but we won't get into detail. So for now, let me switch to entanglement. So instead of having just one qubit, let's consider 2-qubit quantum systems. So we have different possibilities for describing the whole system. We have what we call product states. So we have 1 qubit that we say that belongs to Alice, 1 qubit to Bob, and the state of the whole system is just the individual state of Alice, tensor product, the individual state of Bob. So with that we have, and this describes the whole state of the system. For example, if I have plus plus, we have just this combination here. And if Alice makes a measurement on her side, it won't affect the state of Bob. But there are other kinds of states that we call entangled states, where, like for example here, the state psi plus, that we cannot express as an individual state for Alice times an individual state for Bob. So that there are really like bizarre states, and they will have strange properties. For example, if we measure them, so let's say we have this state psi plus, and Alice and Bob, they make their measurement in their own labs. So let's say they have several copies of this state. So Alice measures in the z basis. Sometimes she will get plus, sometimes she will get minus. And then Bob does the same. So each one in their lab, they just have their sequence. But then when they compare their result, they will get perfect anti-correlation between their results. Because each time Alice gets outcome +1, then Bob will have outcome -1, or vice versa. Each time Alice has outcome -1, Bob has outcome +1. So that's a very bizarre property of quantum mechanics. It's as if the 2 qubits could communicate at a distance, because this works at arbitrary large distances. So this is a very strange property that even Einstein couldn't believe at his time. And this is one beautiful property of quantum mechanics that allows to do a lot of interesting things like quantum teleportation, for example, or things like that. But I will finish here for now. So thank you for your attention.
Okay. Thanks a lot for the introduction, Matthias, and thanks to you and the organizers of the Quantum Club for inviting me here and giving me the opportunity to tell you about my research. I really think this Quantum Club is a great initiative, so I'm very happy to be here. So today I want to tell you about dynamics and phases of quantum information, the same type of quantum information that Matthias was telling you about. And the goal in this talk will be to kind of explain and define what I mean here, and to hopefully give you an idea that this is an exciting and timely field. Okay. So most of my research is about what I like to call far from equilibrium quantum matter. Okay, and so what I mean by this is I tend to work on systems that are quantum, have many, many degrees of freedom, and are driven far from thermal equilibrium. Okay, meaning they won't be well described by things like thermodynamics or equilibrium statistical physics. Okay, so you cannot well define them. You cannot describe them well with, say, a temperature. Okay, and so I tend to work on many different questions. Of course, I don't expect those words to mean a lot to you. But in this talk, I will instead try to give you a big picture of what the main questions are and address at least some, or maybe give you an idea of what some of the questions are. Okay, so many of those questions that I work on are really motivated by the advent of those new experimental platforms that we have around these days that you can think of as small-scale quantum computers. Okay. And so those platforms, I'll talk more about them later. They're very different from the type of systems we usually think about, at least in condensed matter physics, which is my field. And you're probably aware that we're undergoing some second quantum revolution in some way, where those platforms are really evolving at some crazy pace. And even though they're still far from being full-fledged quantum computer that will maybe change the world, they are definitely amazing physics experiments, okay? And I will try to convince you that they raise new interesting questions. Okay? And so in particular, my goal will be to try to tell you about what replaces the notion of phase of matter in those systems. Okay? So when you think of a phase of matter, you think of maybe liquids, gases, maybe metals, maybe magnets. Okay? All of these are notions that are built on thermodynamics or equilibrium statistical physics. And this is really a regime that's, all those platforms operate in a regime that's very far away from this. But nevertheless, I'll try to convince you that some of ideas of like classifying things in terms of phase of matter still works in those systems, even though they are very far from equilibrium. Okay? And I'll talk also a bit about what I will call universal phenomena, and I'll explain what that means. Okay. So here's a brief outline of the rest of the talk. So before I talk about things that are far from equilibrium in those platforms, I will actually take a step back and just talk about condensed matter physics. You may have heard about condensed matter physics before, but again, I assume we have a broad audience, so I just want to make sure we're on the same page. I'll talk about what the big goals of that field are, because that's really the same goals I'll be pursuing when talking about non-equilibrium systems. And I will also highlight the role of entanglement in those systems, okay? And then I'll move on to those devices or new platforms that are often called noisy intermediate scale quantum devices. Again, those small scale quantum computers that we have around. And I'll explain how they define kind of a new regime of quantum dynamics that I like to call interactive, and I'll explain what that means. And then finally, hopefully I'll say some words about those phases of quantum information that I was promising in the title. Okay. All right. But let me start very basic. So I think of myself as a condensed matter physicist, even though I don't work on materials. Okay. So what is condensed matter physics? Well, you can ask Wikipedia or ChatGPT or something. This is a slide from quite a few years ago, so using Wikipedia. And you can find this definition. So it's the field of physics that deals with the microscopic properties of matter, in particular the condensed phases that appear whenever the number of constituents in a system is large and the interactions are strong. Okay, so it's maybe a slightly debatable definition, but it's a pretty good one if you ask me. And roughly speaking, it's the field of physics that deals with the collective behavior of systems with a large number of constituents. Okay? Notice that the word quantum doesn't appear in this definition. So in principle, it could also include like things like biological systems or things like you have on this slide, okay? It's sometimes also referred to as soft matter physics, okay? But I would think it's a part of condensed matter physics as well. But okay, this is a quantum club, and I'm talking about quantum things. Quantum condensed matter physics is also sometimes known as solid state physics, right? And the physics of materials, which is very rich. So you can have pretty complicated microscopic systems and very varied phenomena. I think it's a field that has a very interesting history. I think one interesting aspect of it is that it hasn't always had the best reputation among at least physicists, like theorists. And I'm putting a famous quote of Gell-Mann, whom you may know is a famous high-energy theorist. He's known in particular for like introducing the concept of quarks. Okay? And so he used to refer to solid-state physics as squalid-state physics. Okay? So if you don't know what squalid means, I put the French translation there. So this gives you an idea of like how well he thought of the field. Okay? Okay, so in a nutshell, he kind of thought that was a messy field, you know, and that was nothing compared to the beauty of fundamental interactions in particle physics. Okay, and okay, I think it's, of course, everyone is entitled to their opinions, but I think it's really an outdated perspective on what condensed matter physics is. A sort of modern picture, I put modern between quotes because it's been ongoing for more than 50 years now, is really to focus on the notion of emergence, okay? Is that you can have somewhat complicated and messy and things that that Gell-Mann didn't like, you know, microscopic physics, where you start from the quantum materials, you have to worry about, you know, atoms and crystalline structures and interactions and so on. But you can have beauty and simplicity emerging when you deal with microscopic phenomena, okay? And again, the reason I'm telling you about this is that it's the same kind of emergent phenomena that I'll be looking for in non-equilibrium systems, okay? What kind of emergent phenomena? For example, superconductivity, right? Or things like, So it's also a principle. It's closely related to something that we like to call universality in physics, okay? We can have some properties that are completely independent of microscopic details. They don't care about chemical makeup, which atoms you use, or things like this. And they don't care about that messy physics that Gell-Mann didn't like. And they kind of fix by symmetries and dimensionality and things like this, okay? And so this simplicity, the idea is that simplicity emerges from this complexity, the complexity of those systems, okay? So in the context of condensed matter, one way we like to understand things is we have different phases, right? So you can say that we have phases such as magnets, superconductors, and things that may be more exotic to you. So for example, there are phases that are known as topological. There's also some special types of insulators known as topological insulators. And we keep discovering new phases like this. All of this is in equilibrium. And one thing that is somewhat interesting here, from a historical perspective, is on the theory side, the universal language that we use to understand all of this is that of quantum field theory. And the reason it's ironic is it's precisely the same language that high-energy physicists and particle physicists use as well, okay? So it is really a cross-disciplinary language, and we use it both to describe the standard model of particle physics and to also understand all those emergent properties. Okay, so I put some equations on this slide that you're supposed to ignore. They'll play no role. But just for the mechanics 2 students, those are Lagrangians like the ones we see in mechanics, okay? So if you want to learn about quantum field theory, it's a very advanced topic. You can take quantum field theory 1, 2, 3 here in Geneva, right? Anyway, so that's the language that we use to understand that. An even more modern language that condensed matter theorists like to use is that of quantum entanglement, okay? So I can go quickly because Matthias already talked about this. Okay, so it's one of the defining features of quantum mechanics. And okay, well, usually when you learn about it, you think in terms of maybe 2 qubits or 2 degrees of freedom. And it turns out, like again, in recent years, when I say recent, again, it's been going on for more than 10 years, but condensed matter theorists have spent a lot of energy and time understanding the properties, the entanglement properties of systems with many degrees of freedom. Okay, so remember those condensed matter systems, you don't have 2 qubits, right? You have many. And we can think about entanglement in those systems, and it turns out that it gives you a very powerful picture in how to kind of classify the different phases, okay? Maybe one that's a bit less intuitive, but it turns out like there are many phases of matter, and most phases of matter you're probably familiar with, that don't really require entanglement to exist, and they're called short-ranged entangled. And those include, for example, just magnets. Okay, those don't really rely, they're less quantum if you wanted, they're more classical phases. But there's also some phases that are intrinsically more quantum and that have what we call long-range entanglement. And so that includes those topological phases I was mentioning, for example. Okay, so they are like intrinsic. So we know that some phases are more quantum than others, and it may not have been intuitive if you want, just looking at them before that. Okay. Okay, so all of this was about equilibrium physics and condensed matter physics. Mostly the reason I'm telling you all of this is I will be asking similar questions now, but in the context of those non-equilibrium systems. So, okay, one message, and you kind of have to trust me here, is that entanglement and other type of quantum information metrics have become extremely popular in condensed matter theory to really understand the properties of phases of matter. It's really a language that we all speak now, let's say. And the rest of this talk will be about thinking of those ideas, but now far from thermal equilibrium, okay? And I'll define what that means and why that's interesting, and whether there's also a notion of universality, okay? Are things messy, like Gell-Mann field, that if you change a bit your system, you have to worry about all the details of your system and everything is a mess? Or are there like universal properties and simplicity that emerges in those systems as well, even though they are like not in equilibrium, okay? So that's the last slide I have about maybe typical condensed matter setup. So if you're a theorist like me, this is what a condensed matter experiment looks like. Okay, so you have your system, that's your like material that you want to study, and it's coupled to some bath, typically. Okay, meaning it's in thermal equilibrium. I should emphasize that this bath is usually there whether you want it or not. Even if you try to isolate your system very well, effectively the things that you want to study will be in a bath, maybe because of phonons, because of nuclear spins. It could come from many sources. But basically, your system will typically be in thermal equilibrium. There are ways to take solid-state systems out of equilibrium, but I won't talk about them here. But typically, you can use things like thermodynamics. And since typically we care about quantum effect here, you work very hard to reach very low temperature, ideally 0 temperature. Okay? We know, from if you take statistical physics, or like if you just take, like, say, a simple harmonic oscillator, if you're at very high temperature, your system will behave classically. And so, if you want to see quantum phenomena, ideally you try to be at low temperature. Okay. So now let's move on to this new generation of devices. So again, they're called noisy intermediate scale quantum devices, or NISQ for short. It's a term that was coined by John Preskill, who's a physicist in Caltech. So all of those devices are, they can be very different. They come from very different technologies. They can be neutral atoms. They can be trapped ions in some way. They can be based on superconducting qubit technologies. I won't go into the details of how they work. But they all have in common that they aim to be small-scale quantum processors or simulators or quantum computers, if you want. Okay. So they can work in different modes. They can be analog or digital. I'll say a bit more about this. But essentially, there are platforms that are very well isolated from their environment, and they are highly tunable and programmable platforms. Okay, so ideally, that's what you want from a computer. You want to be able to program it. You want to run a program on it. Okay, so you want to be able to tune the interactions both in space and in time at will. Okay. And that's what all of these platforms are trained to do, okay, in a nutshell. So they are still noisy, that's the N in NISQ. And intermediate scale refers to the fact that, they're in the range of like dozens to hundreds, going into the thousands of those qubits that Matthias was telling you about, okay? That's either a lot or not a lot, depending on your perspective. That's compared to like a solid state system, that's very few degrees of freedom, okay? But that's still way more that you can simulate on a classical computer at this point, or at least it's getting into the regime that's very hard to simulate. Okay, so typically on a classical laptop computer, you can simulate 20 to 30 qubits. Okay. Okay. And so when you think about those platforms, The protocol is very different, right? So I had my cartoon picture of what a condensed matter or solid state experiment looks like. Now the cartoon is very different. So for those platforms, the protocol is you prepare an initial state that you control. Typically, this will be a very classical state, like one of those product states. And then you will run some type of quantum evolution, okay? So that evolution can be analog, meaning it could be like solving Schrodinger's equation, but with some Hamiltonian that you control very well. Okay, so meaning you can really design all the interactions that you want, and you can evolve it in time or things like this. Okay, or it could be digital in a sense that you could prepare your initial state, and then you have a series of quantum operations that are known as quantum gates that you can think of as, you know, certain qubits will interact for some time, again in a very controllable way. Right, so you can really design the interaction that you have, and this replaces what the classical gates that you would have in a classical computer. Okay. And then at the end, or like as you go, you would measure things. Okay. So notice like when I describe this protocol, I have no temperature, right? I just have an initial state and some dynamics. That's the protocol. Okay. You prepare something, you run a program, and then you measure something. Okay. So we want to understand like this general dynamics here. So I mean, maybe one point I should have emphasized that I see here is like I should really emphasize the pace at which those experiments are developing is pretty amazing, if you ask me. Like literally, if you look at the state of many of those platforms 5 years ago and where they are now, they're really developing at some alarming pace. Okay, it doesn't quite mean you'll have quantum computers that will again change the world tomorrow, but definitely they are very impressive, you know, quantum experiments that run in regimes that are very far from traditional solid-state systems, and that's the perspective I'll take today, that I like to take in my research. And for theorists like me, they also raise new challenges and questions. Okay, so the main question is how do we understand the dynamics of such systems? So I mentioned that for condensed matter physics, you know, we had that universal language of quantum field theory and things like this. All of this is out of the window because they are in a regime where this doesn't apply typically, right? So we're really thinking about dynamics here. We cannot use low temperature, low energy physics in the way we do in equilibrium systems. So you have to come up with new tools. In particular, can we even think of a notion of phase of matter? For example, what does that even mean? Because those systems, again, are not in thermal equilibrium. Are things messy or universal? Does it depend on all the details of what you do or not? Right? Can we kind of classify different type of dynamical evolutions? Okay, so those are just two examples from my research. They're like very biased because I'm involved. Those are experiments I'm involved with. But just to give you an idea of what I mean of like type of things that we can realize, you know, the point of view that I have is like, again, those platforms, even if they're very far from being fault-tolerant quantum computers that can factor primes and break your RSA code, and they are definitely very different, again, from traditional condensed matter experiments, and so you can really access things that you would, or regimes that you would not be able in traditional solid-state systems. So just to give you an idea, like in the first paper, we realized a new phase that we call dynamical phase. It's, you know, we were able to really show that it was a phase in the sense that it was robust to perturbations. And it was one of those topological phases that I told you about in equilibrium physics. But it's one that we realized in a system that was driven in some kind of crazy way with all sorts of pulses, completely far from equilibrium. It was, you know, think of driving your system left, right, and center all the time. So completely in a regime where there was no hope of any equilibrium description. And in fact, the type of phase that we could realize is something that was forbidden to exist in equilibrium. So you can actually realize something that was fundamentally could not exist in a ground state, or something like that is described by the low temperature physics of some Hamiltonian. Okay. In that more recent paper, we were studying how things like hydrodynamics, so fluid-like behavior emerges from strongly interacting quantum systems. Here, like the idea was that we're using unique capabilities of those platforms where you can individually image particles. You can kind of follow them around, which is not something you can do at all in a solid-state system. Okay, and the things that we could measure there, I say we, I mean my experimentalist colleagues could measure are really things that, again, would be completely impossible in a traditional solid-state system, okay? So it's not that those platforms are better, right? They just allow you to measure different things, okay? Okay, so in the time I have left, I want to actually think a little bit more of those platforms in the way they are designed. That is, they're designed to be processors of quantum information, and that will actually lead to a broader notion of phase again, okay? So all of these platforms, like I mentioned, they are, you can think of them as quantum simulators. You kind of simulate some type of quantum evolution. But really, they all have the goal of being quantum processors, like I mentioned, like things that can run a quantum program in some way, okay? I should say that most of the major experiments are in non-academic labs, okay? Actually, the ones I mentioned briefly, okay, sorry, I will have to go back too early, but yeah. Like some of the pictures I had earlier were from a lab in Google and from Quantinium, which was from Honeywell before. So they are in non-academic labs, and their goal is to do fundamental physics, but also ultimately they would want those platforms to be actual quantum computers, okay? So what's the problem then? So the problem is all of those platforms are kind of noisy in some way, and you have to correct the errors that occur, okay? So here's kind of a general diagram of how you should think about those systems. So what we want is something like this. So we like to have, in quantum information, we have to have people that have names like Alice and Bob, typically. And so what we want is something like this, where Alice has some quantum information in the way Mattia has defined. So it could be a bunch of quantum states or qubits. And she would like to run some kind of quantum program on those qubits, perform some operations, and then Bob would like to recover that information in some way, right? So typically, in order to avoid errors, I'll say a bit more about this. What you would want is like encode that information in a larger system. Okay, I'll say more about that again, and run that program, and Bob would do something. Bob would do something, hopefully, to recover some information that was transmitted. So one issue is that there's, no matter how amazing those platforms are, there's always some coupling to some environment, some noise that you don't control, okay? That's the N in this NISC. All of these platforms are somewhat noisy, okay? There's always some coupling you don't want. And so what it means is that you have some errors that will occur, okay? This also occurs in classical systems, right? So you have like classical bits, 0, 1, 1, 0, and you could imagine that your environment is taking one bit and flipping it. So one bit that should be 0 becomes 1, okay? So the way you can deal with it in classical information, so there's an entire field, right, based on this, that's known as classical error correction. But one maybe intuitive idea you can go around this is to repeat the information, okay? So that's known as repetition code. So you can take your qubit, you can take your classical bit, which is 0, and you can copy it many times, say 10 times, you have 10 zeros. Now, if you have an error and one of the zeros is flipped to 1, you can still look at your 10 bits and see that you have 9 zeros and 1 1, and you can guess that maybe the one that was flipped was an error and correct it, okay? Does that make sense? Yeah, so you're pretty basic. So it's called, you just repeat the information, you copy it many times, and then you use a majority rule, okay? Okay, ideally you want to do something like this in quantum systems. And it turns out it's pretty complicated for many reasons. So one of them is you cannot copy quantum information. There's a theorem known as no cloning theorem that you cannot do that. And there's also all the complications that Matthias mentioned, that if you measure a quantum state, you will also affect your states. It's part of the dynamics. So you want to make sure that whatever you measure, you don't destroy the information you were trying to protect in the first place, okay? Okay, but nevertheless, there's an entire field known as quantum error correction built on this idea that we should correct the errors that occur, right? And the idea is that, okay, you cannot just do this. You should also have Bob measure the system as you go, kind of check if some errors occurred, and then based on what you measure, perform some feedback to correct the errors. Okay, does that make sense? So you at least at the cartoon level, that sort of makes sense, yeah? Like you just check, did I have an error, correct it, and you keep going, okay? And this is something that will have to occur in any of these platforms, right, in order to have something that would resemble a quantum computer, because those errors are always going to occur, so you need to correct them. Okay. So if you think about this, so this is kind of, again, big, like a theorist cartoon picture of what quantum error correction looks like, okay? But if you think about it as some kind of general level, this is the most generic and complicated type of quantum evolution that you can ever think of. Because you have some initial states, it runs through some dynamics, which is noisy, so that's what we call the open quantum system. And on top of it, we measure it. Measurements in quantum mechanics also affect your states, so that's part of the dynamics. And on top of it, we also perform some feedback based on what we measure. Right, so you imagine you run your experiment, you get some data then you post-process it on a classical computer, and then you modify your experiment as a result. So you kind of have a feedback loop on this, okay? That's by quantum evolution, okay? And as theorists, we like to make things even more complicated. So we usually like to think for conceptual levels, that there's even one more person there. There's a person that we call Eve, who's eavesdropping, like think of Eve as hacking into the computer of Bob and getting the data that Bob was measuring. So that seems kind of a messed up scenario, but it's just imagining that Eve doesn't know anything about the platform, she doesn't have access to it, but she has access to whatever you measure and whether she can tell anything or not. Why is Eve required? Well, it turns out it tells you a lot about your ability of your system to protect information or not. Okay, so that's a complicated picture. So it's a very general and complicated quantum evolution. As I said, it's probably the most complicated quantum evolution you can ever think of. And now it's really phrased in terms of information, right? What you want is to preserve that information through that process, okay? And again, like now, me and many others are looking at this as a problem of condensed matter physics, where we're trying to think whether we can think of phases of matter that are now in terms of information. Are there regimes where the information is well protected or it's not well protected that we can? Are there regimes in which Eve can learn something, for example? Are there regimes where you can correct? There's a sense in which you can think of these as phases of matter, okay? Okay, and I keep repeating the same thing over and over, but again, one question that we're really asking is everything super messy, or again, is there some beauty or simplicity emerging from all of this, okay? And I don't have a full answer to those questions, right? But the early signs that we have is, yes, we can import many of the concepts and ideas that we know from condensed matter, and no, things are not messy, and there's a lot of universality and beauty that emerges in those systems, okay? So just to give you, like, that will be basically the last thing I say in this talk, just to give you one concrete example, okay? So in recent years, we, and I say we as a community, it's not just me, like started thinking about what we call phases of learning, okay? Meaning that there are some systems where you can have different phases, and I put phases between quotes, that are characterized in terms of how information is kind of hidden or not from monitoring a system. Okay, so what do I mean here? So this diagram was kind of very complicated. So again, in theory, we usually like to simplify things. So let me forget real life and imagine there's no noise. And just imagine you monitor a system, okay? Measuring a system is already complicated in quantum mechanics because it modifies it, okay? So again, that's something that Matthias explained, right? If you measure a quantum system, that affects its wave function. So it's part of the dynamics. So now imagine a quantum system. So it could be a bunch of these qubits, and you perform some quantum evolution. That's this blue box. So time is running in the vertical direction here. And you have some quantum evolution, this blue box. This could be your favorite Hamiltonian or some of this quantum program that we're trying to run. And then on top of it, we're going to measure some of the qubits. Okay, those are the little boxes here. That's a symbol for measurement in quantum information. So you just measure those qubits. You measure if they're 0 or 1, say in the Z basis. So you get some classical information, zeros and 1, and that's, we're going to call Eve the observer here. Okay, so Eve is just measuring the system. Okay. So this is just a very general setup. I'm just telling you there's some quantum dynamics, and then you monitor or you measure some of the system as you go, okay? And you don't measure the whole thing, you just measure some of the qubits some of the time, okay? And so it turns out in this very general setup, we actually think they are phases of matter, but they're not phases in the usual sense. It's not something where you can, check that it's a magnet or not, or whether you can run a current through it or not. Like you have to actually think in terms of information to think of those phases. There are phases that are characterized in terms of how much Eve can learn from measuring the system. Okay, so that seems a bit weird, but there's a phase in which basically if you don't measure the system enough, Eve learns nothing, and the information remains hidden in some way. Okay? Whereas there's a phase in which Eve can actually extract information from the system and learn from it. Okay? What does that even mean? Well, it's really the same type of questions we're asking here, right? We're trying whether we can protect the information from the environment. Okay? If the environment can destroy your information, you kind of lose it, basically. And so this is kind of a baby example of this, where we're basically asking whether the information remains in the system or whether you can learn it from measuring your system. Okay, and it turns out it's an actual phase transition in between. Okay, just like the phase transitions you have between the phases of matter you're familiar with. Okay, so that's the only actual plot of this entire talk. But this is again to make this slightly more concrete. So how can we see this? Well, for example, you can play the following game. You can imagine that you have two initial states that are complicated wave functions of many qubits. Okay, I'm going to call them psi0 and psi1. Okay. And let's say those states are orthogonal and complicated. You cannot just measure one qubit and say which one is which. Okay, they're very complicated, highly entangled wave functions. And Alice has those two states, and she'll pick one at random and run it through some dynamics. And now you have Eve, who's like measuring the system, getting some data like zeros and ones. And Eve's goal is to guess what initial states Alice started with. Okay. So again, it seems I phrase it as a game where you can think that Eve is an eavesdropper. Again, she's getting partial information and she want to get some information. Okay. And the question is, can Eve actually guess what initial state you started with? Okay. So that seems like a weird setup. As a function of something I'm going to call gamma, which is the measurement rate, how many measurements Eve is allowed to make. So if gamma is 0, Eve doesn't measure anything, so she doesn't learn anything. But if gamma is near 1, she measures the system all the time. Okay? So what's plotted is the accuracy of this procedure, so that is the probability of success of Eve to distinguish the two states. And what you're seeing in this plot is actual numerics from relatively small systems. L is the number of qubits. And when gamma is small, what you see is this probability of success is near 1/2. Okay, and that makes sense. So you're trying to distinguish two states. I picked one at random. So probability 1/2 means that Eve is just flipping a coin. Okay, so she's just flipping a coin at random, says, I have no idea, and like, okay, and sometimes she gets it right, sometimes she gets it wrong. Okay. But as you increase the measurement rates, she starts to do better than flipping a coin, okay? Because she's getting information from the zeros and ones that she's getting, and she can do better. So what's plotted, I'm not telling you how we actually do this, right? So there's an algorithm that we call decoder. What I'm plotting is actually the provably best that Eve can do. So that's kind of the optimal result that Eve, that's the best, with the best algorithm in the world, that's what Eve can do, okay? But okay, so what actually happens, so if you measure a lot, well, this probability of success actually doesn't go to 100%. She can never do 100%, but it goes to 75%, which is better than flipping a coin. Okay, so you're getting some information, at least whereas here your measurements are basically telling you nothing. It's kind of random garbage, yeah. And so what you're supposed to see is like there's a crossing in those different, as a function of system size. There's an entire regime where if you increase system size, here this probability of success goes down. And there's another regime where the probability of success goes up as you increase the number of qubits. And so I put a dashed line to guide your loving eyes of what will happen if I took L very, very large. Okay? And so we know this also from theory. There's an actual phase transition here, meaning there's an entire regime here where there's a phase really where, again, Eve would learn nothing from measuring the system, whereas if you measure more, whereas if you're above this threshold, Eve will start to learn and have information. And the critical point in between is really the same type of phase transition that we're used to in condensed matter physics, okay? And in fact, the tools that we use to understand those things are the same type of tools we use in equilibrium condensed matter physics, okay? And so the bottom line is, like, again, that may seem pretty abstract, but this is, thinking in terms of information is precisely what you need for those platforms, okay? And really distinct phases of matter, but again, they're not like liquids or metals or magnets. They're really characterized by information, by whether the information is kind of hidden from someone measuring the system or whether it kind of can be revealed and whether you can learn from it, okay? I mean, it also tells you that, basically I'm telling you, you have a quantum system, you measure it, there's an entire regime where the data you get is garbage. It's telling you nothing about the state of your system, whereas there's a phase where it actually tells you something, okay? And so those are phases, okay, that are characterized by those properties. And there's lots of, this is entirely universal in the sense that it doesn't depend on, you notice I've been very vague about what the actual system does because the details actually do not matter, okay? So this is a new type of phase transition that's rooted in the foundation of quantum mechanics. I only need quantum evolution plus measurements to have this. And maybe the last slide I'll have in this talk is to just give you an idea of like what we do on the theory side to deal with this. Okay, how do I know this? This was exact numerics, okay, what I showed you. How do we understand all of this? It seems like a pretty hard problem. Everything is in non-equilibrium. We're talking about things like information. And one thing about measurements in quantum mechanics is they make the evolution nonlinear. So again, it's pretty complicated. But this is where like some magic happens. It turns out, so this is actually my work here, or at least I've been working a lot on this. There are like surprising connections between those out of equilibrium quantum information questions and things that are classical looking and that looks like classical statistical mechanics problems, okay? So I won't go into any of the details of this. I will just claim that's true, okay? So the point is you can have surprising connections between, say, entanglement and, say, the physics of a classical polymer moving in a random medium, okay? Two problems that have nothing to do with each other, but somehow surprisingly, they are related, okay? And we have lots of those mappings now that we understand. And one problem is quantum, the other is classical. It doesn't really matter. They are mappings, and so we can use them to understand those things. Okay. And yeah, okay, that was maybe a picture of this. So for example, entanglement is also related to what we called domain walls in a classical magnet. Okay, I won't go into the details of this. If you think of a uniaxial magnet, you can think of it as a collection of moments that are either pointing up or down. Okay, so you can have, if you have a region where all the magnetic moments are pointing up and a region where they're all pointing down, you have a domain in between. Okay, that's called a domain wall. And this can have a line tension. This costs some energy. Okay, you just have to trust me that this is, physicists have studied this for many decades. We know a lot about domain walls in magnets. And for some reason, it appears to be related to quantum entanglement out of equilibrium in those systems. Okay, so again, not asking you to understand the details here, but the only important point is like there are very surprising emerging connections between quantum information sciences and basic condensed matter or statistical physics. And it kind of goes back and forth, right? And in that way, physics is always beautiful. You always have those unexpected connections between very different fields. Okay, so with this, let me wrap up. If there's one take-home message is that quantum information, I think, has become kind of a new language to understand and classify phases of matter in condensed matter physics. That's also true in equilibrium, but also out of equilibrium. When thinking about those new experimental platforms, there are many new challenges for theory. I've highlighted like thinking of what it means to have a phase. I haven't really given you an answer, by the way, right? But this is just a general question we have, right? Of how we define a phase of matter for non-equilibrium systems. We just have like bits of pieces of the answer. And whether, again, things are kind of universal, whether all the things that we know about condensed matter also apply there, okay? But one direction that I'm excited about is thinking of what those platforms really are about, which is thinking of open quantum systems where you have errors and you have feedback and you try to correct errors and you think of information. And even then, it seems like thinking from a quantum matter perspective is helping us understand different regime. Okay? And there's those phases that we call, again, characterized by learning that many people, including myself, are exploring. And yeah, with this, thank you very much for your attention.
Thank you very much, Romain, for this very nice talk. So thank you very much, Matthias, for your introduction. We are preparing the apéro, of course. But we already have some questions now.
Thank you for the talk. Excellent. I have a question about the guessing game that you were showing.
Yeah.
Why we cannot go till 100%? Actually, why there is a limit on 75%?
Yeah, thanks. That's a very good question. So it's related to one thing that Matthias was telling you about, that when you measure your state, you destroy it. So one thing you could do is say you have those two states. One thing that you could do is let me measure every single qubit in one go. Let me forget dynamics. Let me just focus. I just measure the whole thing. Okay. What you will get is, maybe you'll find the first qubit is in state 0, the second is 1. You'll get what we call a bit string of you'll get now a classical state of zeros and ones. Okay. But that doesn't tell you which state it is. In a sense, it's only one of the exponentially many states you could have. Right, so your quantum state is a superposition of exponentially many such. Okay, so you're getting very little information actually when you do this. Like in the sense that you could have gotten the same outcome from that state as well. Does that make sense, right? Like if I measure this, that's again, I think Matthias had a similar example in his 2 qubits. You could get a measurement outcome here, and you could get exactly the same measurement outcome starting from this state. And actually, if you repeated the experiment, you would surely get a completely different outcome. Okay. So actually, the surprising thing is you learn anything because it's actually very little as you have many qubits. But it turns out like if you play this game by just measuring the whole thing, you can show that you can actually still distinguish states with 75% accuracy, which is better than 50%, but it's definitely not 100%. Yeah, and the issue is once you've done this, you've destroyed your state. Right, so the way I'm doing this protocol is you get one shot. That is, you measure and that's it. You have to make a prediction. You don't have 1,000 copies of the same state that you can repeat the experiment many times. So once you measure, state is dead. You have to make a prediction. Sure. Yep.
And when another decoder who's error corrector or something, I don't know what he's doing, he's not measuring the state. He's not destroying the information.
Yeah, good. So here, I didn't tell you what this guy was doing, Bob. Yeah, so you have to measure, so in this whole field, you have to measure things in a very careful way. So you don't destroy your quantum information, but you still learn about whether errors occurred. And it's possible to do, right? So this is good news. People have thought about this. So you can measure some operators that are carefully chosen to tell you whether an error occurred, but you don't want to measure your information itself, otherwise you'll kill it. So that's the subtleties with quantum mechanics, right? Like that's why this whole field of quantum error correction is so intricate versus classical error correction.
Yeah. Do we have other questions? All the rest was perfectly clear.
Sure.
You talked a lot about phases.
Yeah.
And normally you have some parameter.
Yep. Yeah.
Temperature, for example.
Yeah. So here it depends, but for example, that could be the strength of this noise, like how much noise I have here, or it could be how much you measure the system. So for example, in the example I gave, it was this measurement rate, like that I didn't define very carefully, but like it's roughly how many measurements you have in your system. So if you measure your system a lot versus not, that's what plays the role of temperature here. Okay, so again, it's different parameters, right? It's, how coupled are you to the environment? How much are you monitoring the system? How much feedback are you performing? Those are your knob. Okay. Yeah.
Thanks for a great talk. Does this rate correspond to some level of multi-parted entanglement in your system? Is there a quantum Fisher information level that you're hitting?
Yeah. Yes. So there are like indeed like in the way I've formulated it as distinguishing states, it's closely related to those ideas. There is also some notion. Yeah. So this phase transition also corresponds to a phase transition in how entangled your state is. So it's also something we call an entanglement transition. So if you want the closest thing to an order parameter, which tells you which phase you're in, is actually entanglement.
It could actually be important for the connection with condensed matter.
Yeah. Yes, absolutely. But yes, like I should say, many of the people that are thinking about the nature of those transitions are condensed matter physicists. Like people in quantum information are more interested in like finding good algorithms to avoid errors or things like this, right? But yeah.
I have maybe one question about that. Like, so do you collaborate with people that do like pure quantum information theory? And if yes, how hard it is? I mean, because it's
Well, so quantum information theory is a huge field, right? So that's, I should also clarify, like quantum information by now is like bigger than many, it's an incredibly huge field. Okay, so there are people working on quantum algorithms. There are people in, computer science departments. There are like, yeah, so I don't collaborate or could talk to all of them, right? I definitely work with people that are like, quantum information, they don't define themselves as condensed matter physicists, they really think of quantum information. And you just have to find a common language. But like I was trying to illustrate some of the language of condensed matter, for example, is helping, and it goes both ways, right? So the language of quantum information is helping condensed matter, and I think it has, yeah, in the recent like 10 to 15 years, I think we've had many examples on the theory side where thinking in terms of entanglement helped a lot condensed matter. And I think we're also getting to a point where like the language of condensed matter is helping some ideas of quantum information. In particular, they have those phase transitions where you lose information versus not. And I guess what I'm trying to say is those are the same type of phase transitions that we used to in condensed matter physics. Yeah.
I guess the apéro is ready now.
Perfect.
So we can thank the both speakers again.
Thanks.